Hey everyone, welcome to this explainer. I'm super thrilled you're joining us today because, honestly, we're tackling one of the absolute most fascinating and, let's be real, sometimes frustrating challenges in modern tech. We're going to demystify exactly how we get artificial intelligence to basically stop making things up and start giving us real, verifiable facts. If you've ever used a large language model and caught it just confidently inventing information out of thin air, you know exactly what I'm talking about. So today, we're lifting the hood. We're going to look at the actual mathematical and architectural solutions that are fixing AI's fact problem once and for all. Let's get into it. But, to really understand where we're going with all this, we kind of have to look at where we started. Human beings just need to know things, right? Pretty much the second computers were invented, we wanted them to answer our questions. Like back in 1961, there was already a system that could answer questions about American baseball stats. Then in 2011, IBM's Watson completely famously crushed human champions on Jeopardy. And today? Well, today we want to ask it massive, complex things like, where does the energy in a nuclear explosion come from? Now, this constant desire for answers actually brings us to a really interesting historical dilemma. Way back in 1864, the computing pioneer Charles Babbage was asked a pretty funny question. He noted that people genuinely wondered, and I'm paraphrasing here, if you put the wrong figures into a machine, will the right answers somehow still come out? It sounds silly now, but it brilliantly hits the nail on the head for our modern AI dilemma. The right inputs are absolutely crucial for getting correct answers. If a language model doesn't have the right facts grounded in its immediate input, there's just no way we can expect the right output. So here is our roadmap for today. First, we'll cover the problem with LLMs. Second, the RAG solution. Third, information retrieval basics. Fourth, the vector space model. And finally, weighting words with math. Okay, let's jump right into section 1, the problem with LLMs and why AI actually hallucinates. So look, while large language models process an absolutely massive amount of facts during their training, and they do actually encode a ton of this factual knowledge right there in the connections of their huge feed-forward layers, they still suffer from a few pretty fatal flaws. First up, they hallucinate. This means they make up responses that completely ignore the actual facts of the world, even when the correct facts are buried somewhere in their parameters. Second, they have a serious lack of calibration. A properly calibrated system knows when it might be wrong, right? But LLMs, they'll often give you a completely bogus answer with absolute 100% certainty. Third, they don't have access to your proprietary data, things like private corporate emails or medical records. And finally, their knowledge is totally static. It is literally frozen in time on the exact date they finished training. To show you just how severe this issue really is, let's take a look at this number. A 2024 study by Dahl and colleagues found that when large language models were asked targeted questions about the legal domain, like specific details about past legal cases, they hallucinated between 69 to 88% of the time. Guys, that is a staggering failure rate. It completely proves that just crossing our fingers and relying on the model to recall stored knowledge from its feed-forward layers, it just isn't reliable enough for real-world factual accuracy. Which brings us perfectly to section 2, the RAG solution, and bringing in external knowledge. Obviously, we cannot have AI just guessing in high-stakes situations. The fix for this is a real game changer called Retrieval Augmented Generation, or RAG for short. Instead of forcing the AI to rely purely on its static frozen memory, RAG uses information retrieval techniques to pull in external, carefully curated documents that are actually likely to contain the answer. Then we essentially hand those documents over to the language model and say, hey, generate your answer based absolutely only on this text. This stops the AI from hallucinating, it grounds its answers in real-world facts, and honestly, best of all, it lets you, the user, actually check the source documents to verify the AI's homework. Plus, it completely solves those proprietary data and static knowledge problems we just talked about. All right, section 3, information retrieval basics, or how we actually go about finding the right docs. Let's take a look at the high-level architecture of what we call ad hoc retrieval. Over on the top left, you start with a massive collection of documents. I mean, this could literally be the entire web, or maybe just your company's private server. All of that gets processed into a massive document index. Then on the bottom left, the user types in a query, expressing whatever it is they need to know, and that gets processed into a query vector. These two separate paths then converge right in the search engine, which mathematically maximizes the relevant score to output a perfectly ranked set of documents. It's like a giant puzzle coming together. So let's break that whole shebang down into 3 distinct steps. First, the user poses a query. Pretty simple. Second, the system doesn't just take a wild guess. It mathematically scores the candidate documents against that query vector we mentioned. And third, the system returns an ordered set of ranked documents. It is exactly this precise, meticulous ranking that gives the language model the exact, highly relevant context it needs to generate a perfectly accurate, hallucination-free response for you. Moving right along to Section 4, the vector space model, where we turn words into numbers. Now, imagine taking a paragraph, let's say it's a movie review, and completely, utterly ignoring the order of the words. We are literally treating the document as if it were a physical bag filled with words, shaken up, where the only thing we actually care about is the frequency. So we don't care at all that the words satirical and humor were sitting right next to each other in a sentence. We just count that the word I appears 5 times, it appears 6 times, and romantic appears exactly once. We then use these frequencies to build what's called a count vector. Let's see how this actually builds up when we look across multiple documents. Check out this term document matrix for 4 of Shakespeare's famous plays. Every column is a document, and every row is a specific word. Take a look at the word fool. It pops up 36 times in As You Like It and 58 times in Twelfth Night, but only once in Julius Caesar. On the flip side, the word battle is super heavy in Henry V, but basically non-existent in the comedies. Just by counting words, we've essentially built these incredibly unique mathematical profiles, or vectors, for completely different texts. And this brilliantly illustrates exactly why we call it a vector space model. We can take those columns of numbers and literally plot them as physical coordinates in space. So if we plot that fool dimension on the x-axis and the battle dimension on the y-axis, look at what happens. The vectors for the comedies, As You Like It and Twelfth Night, stretch way out along the fool axis and tightly group together. The histories, Julius Caesar and Henry V, shoot right up along the battle axis. Documents that are similar in meaning literally, physically grouped together mathematically in this space. How cool is that? Finally, let's head into Section 5, weighting words with math, moving beyond just raw counts. So look, counting words definitely gets us really far, but it's not perfect. We actually have to contrast those raw counts with what we call log frequency, which is a super key part of formulas like TF-IDF. Here is the intuitive leap you have to make. If a word appears 1 time in a document, sure, it's relevant. If it appears 10 times, it's definitely more relevant. But if a word appears 100 times in a document, does that actually make it exactly 100 times more relevant to the overall meaning than if it appeared just once? No, of course not. The importance tapers off. We absolutely need a way to scale these counts so they don't just completely overpower the whole system. And that brings us to this incredibly elegant bit of math. Term frequency equals 1 plus the log base 10 of the count. It sounds complex, but it's actually super simple. If a word occurs 0 times, the weight is 0. But if it occurs 10 times, the log of 10 is 1 plus 1 equals a weight of 2. If it occurs 100 times, the log is 2, giving a weight of 3. 1,000 times, that gives a weight of 4. You see what's happening? We're mathematically squashing massive word counts so that they scale perfectly, ensuring the search engine balances all the terms in your query to find the absolute best, most relevant document. By grounding AI in these robust mathematical retrieval systems, we are entirely changing the landscape of what this technology can actually do. We're moving from just blindly hoping the AI remembers a fact from its training data to mathematically ensuring it has the correct document right in front of its virtual eyes. So I'll leave you with this final thought. How will combining the incredible conversational creativity of large language models with the rock-solid mathematical accuracy of information retrieval change how you search for truth tomorrow? Thanks so much for joining me on this explainer, and remember, keep asking the right questions.